So for number 56, we want to see if this sequence here, if it converges. And now sequence AN, it converges if AN, it tends to a number, so it has a limit as n approaches infinity. So what we're going to do here is we're going to try to take the limit as n approaches infinity of negative 3 to the power of n over n factorial. And so what we're going to do here is let's just split out this negative part so that we can analyze it separately. So this is going to be the limit as n approaches infinity. I'm going to split off the minus 1 to the power of n and then times the limit as n approaches infinity of 3 to the power of n over n factorial. So these are the same thing, and all I've done is I've split them up into two parts so that we can talk about them individually. So for the first part, this limit as n approaches infinity of negative 1 to the power of n, well, this, if we plug in n is equal to 1, we're going to get minus 1, n is equal to 2, minus 1 to the power of 2 is positive, n is equal to 3, minus 1 to the power of 3 negative, 4, minus 1 to the power of 4 positive, and so on. And so this, we can see here that it just oscillates between 1, negative 1, 1, negative 1, 1, and so on forever and ever. So this doesn't actually have a limit, right? So that is a problem for us. So we're just going to leave this aside here, and we know that this oscillates between positive 1 and negative 1. And now we are going to look at the second part. We're going to look at the limit as n approaches infinity of 3 to the power of n over n factorial. And so if we evaluate this 3 to the power of infinity, that's going to give us infinity on the top, and then infinity factorial is just infinity. So this gives us infinity of infinity. However, so this is indeterminate form, right? This is L'Hopital form. However, we can't use L'Hopital because we can't differentiate this factorial. It doesn't work. So it means that we're going to have to be a little clever and use other tricks. So what we can do here is we're going to use the squeeze, also known as the sandwich theorem. And this theorem here says that, I'm going to show it to you using functions, but it also works using sequences, right? So actually I'm going to show it you using sequences. So if I have this sequence here, and this is our this is AN, and we can see that the AN, the limit as n approaches infinity, this is going to tend to some particular place here, which is called, we'll call this L, okay? So that's our AN. And then we're going to take a sequence that is less than AN, okay? And maybe we're going to call this one BN. So we're going to say that this one goes like so. And we can see here, if this is our Bn, and the limit as n approaches infinity of Bn, that is just going to be infinity, right? Oh, sorry, not infinity, that's just going to be L. So this is L, and as An, as it approaches infinity, this is also equal to L. So what's the point here? Is that we're saying, hey, An is bigger than Bn, right? And An tends to a limit L as n approaches infinity, and so does Bn. Well, now if we have a sequence here that's in the middle of them, that's less than An but greater than or equal to Bn, so maybe it goes like this. Here, and maybe we have here, and then here, and so on. And so we can see that if this sequence Cn, if it is sandwiched, if we say, okay, if it is less than or equal to An, and bigger than or equal to Bn. And we know that the limit of the one above is L as n goes to infinity, and the limit of the one below as n approaches infinity goes to L. Then we can say, limit as n approaches infinity of Cn is going to also be equal to L. It just means that it's sandwiched between these two, right? And so what we have to do here, we have to sandwich this this sequence here between two sequences that we already know the value to. Okay, so once we have this, let's just think about how this works. So this sequence here, it goes, actually, let me move it to the side. So we have here that an is 3n to the power over n factorial, right? So that's going to be, on the top is just 3 over and over and over. So, and on the bottom it's going to go 1, 2, 3, 4, 5, and so on. So it's going to be, and all of these are multiplied, right? So 3 over 1 times 3 over 2 times 3 over 3 times 3 over 4 times 3 over 5, and so on. And all of this until we get to 3 over n minus 1 times 3 over n. So that is our an, right? This is what it looks like. And we can clearly see that all these terms are positive, right? So no matter what our n is, our an is definitely going to be bigger than 0. So that is one thing that we can say. So we can say here that an is definitely greater than or equal to 0. And now we have to find a sequence that an is less than, so that we can sandwich it, right? And so let's compare this to the sequence. Let's compare it to the sequence. Let's see, 3 over 1 times 3 over 2 times 3 over 3 times 3 over n. Let's compare this. Well, these terms here, they are the same, right? So this is the same, and these three, they are the same. But the only difference here is that all the stuff in the middle, if you can see here, we're going to have 3 over 5, 3 over 4 times 3 over 5 times 3 over 6, and so on until 3 over n minus 1. And we can see that at this point, the denominator is going to be bigger than the numerator, right? So we can say that 4 times 3 over 5 times 3 over 6, and so on, until 3 over n minus 1. This is definitely less than 1, because we're constantly multiplying by a number less than 1. So here we would be multiplying by 0.75, 0.6, and so we keep multiplying by decimals, and we are definitely going to get something that's less than 1. So we can say here that, that our an is definitely less than this sequence here. And this sequence here is 3 times 3 times 3 times 3. So that is going to be 81 divided by 6, or it's going to be 27 over 2. 27, let me rewrite this, 27 over 2n. These are the same, right? So as we've shown here, that an is definitely less than 27 over 2n, because 27 over 2n is the same thing as the one on the left, except the one on the left, it has all these terms here that are less than 1. Okay, so once we've established this, we can now go back and say that, okay, let me move over this around. So we're going to say that 0 is less than or equal to an, which is less than or equal to 27 over 2n. So now we're going to take the limit of these separately, right, as n goes to infinity. So the limit as n approaches infinity of 0, well, this is just 0. No brainer there, right? And the limit as n approaches infinity of 27 over 2n, this is going to be like 27 divided by 2 times infinity. So 27 divided by infinity, this is also equal to 0. So hey, what has happened here is that we have shown that an is sandwiched So it's sandwiched between two different sequences, right? The sequence 0, or two different values, 0 and the sequence 27 over 2n. And so given this, because it's sandwiched between these two, and both the, and I'll do that in a different color, and both the outer one and the inner one, they tend to the same place, they tend to 0, so it means that the middle one, an, it also tends to 0, right? And so we have that this limit over here, we're going to say, therefore, the limit as n approaches infinity of 3 to the power of n over n factorial is equal to 0. Okay, so if you remember here that the limit is going to be this guy over here, right? Actually, let me do that in a different color. The limit is going to be this guy over here, which oscillates between -1 and +1. So it just goes -1, +1, -1, +1, times this guy over here, which is 0. So it doesn't matter if it's -1 or +1. When you multiply it by 0, this is still going to go to 0. So we can say that, therefore, that the limit as n approaches infinity of -3 to the power of n divided by n factorial, this is equal to 0. And so, with this being said, we say that an tends to 0 as n tends to infinity, so an converges. And that is it for our number 56. We just broke it down to two parts. We took the limit of the first one, that was the limit that goes 1, -1, 1, -1, and so on. And the limit, and we divided it, actually we were multiplying by the second one. This limit is 0 by the squeeze theorem. And so we see that the limit of the whole thing is 0.